So we've all worked with lazy programmers. Who's not worked with lazy? We all have worked with lazy programmers, right? People that write stuff like this, double quotes plus vol, to convert an int to a string, right? And we all know that that's bad, right? Who thinks the first one is a great idea? Anybody? No, I didn't think so. One person, okay. One lazy guy. Don't work with him. Don't work with him. Find somebody else to work with. And if you look at this, what is the best way to convert an int to a string, right? You could have integer.toString, integer value of, string value of, integer.getInteger. What's the best way, right? Now, similarly, what's the fastest way to convert a string, to build up a string? Like you want to build up a web page and you've got all these different values you need to put in there. What's the best way? What's the fastest way? So who thinks the first one's the fastest, append basic? Who thinks that's the fastest? Okay, like 2 people, 3 people. Who says that append StringBuilder is the fastest way of doing it? 1 only. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Great. Who thinks that the third one is the fastest? And let me just explain that before we ask the question. Basically, when you make a string builder, you're constructing an array of size 16, and then whenever you run out of space, you make it bigger and bigger and bigger. So with this one, you upfront know, with the third one, you're upfront what the size is going to be, and then you don't have to grow the array. So who says the third one is the fastest? All right. Okay. And who thinks the last one? The last one, what we're doing is we're making a regular expression. So you've got all the costs of regular expression, parsing, and so on in there. And then, then you can generate the string. So who thinks the last one is the fastest? Anybody? 1 or 2 people are very confident in the regular expressions of Java. It's not Perl, it's Java, right? Okay. All right. Let's go back a few years to when I first started programming Java. And in those days, they had 3 fields inside the string. There was a char array, and they wrote it in a funny way because these were C programmers who made Java. They had an offset and a count. And the idea was if you made a substring of a string, they didn't have to make a new array. They could simply share the same array and have a different offset and length. So this was fantastic. And that's what the offset and count was all about. Now what was quite funny is they had this hash code function that if you had more than 16 characters inside your string, then they would sample only 8 of the characters and use those for the hash code. So you could have a string of 1,000 characters, and they only look at 8 of those characters. Now, I remember looking at the code, and the way I read it, I thought, oh, they're looking at every 8th character. No. They just look at 8 characters in total. This was back in the day. And equals was also funny. They didn't check whether object equals this, which is an obvious optimization. And in turn, use a static hash table. So that was a nice possible memory leak. At the time, we didn't really worry too much about that because, Java was not the fastest thing out there. And we would never have imagined in those days that we'd have conferences like this where we've got thousands of people who want to do Java. At the time, string buffer was a modifiable thread-safe version. And basically, it's a bit like having a vector of type char. That's what your string buffer is like. And we'll talk about the other versions in a moment. And when you said toString on a string buffer, it actually shared the same underlying char array with the string. Now, we know that string you can't change, and string buffer you can change. So when you made toString, you got the char array off the string buffer, but then when you changed the string buffer after it, it made a copy of the char array inside the string buffer. So it all worked like magic, right? This is what the hash code looked like in string 1.0. And basically, if it was less than 16 characters, then they simply added them up with some magic number times 37, right? And if it was more than 16, then they only looked at 8 of the characters. So they had a skip, which was length divided by 8, and they would simply skip over all the characters and just look at 8 of them. And you can imagine that the hash code wasn't very distinct. It wasn't very unique. Oh, by the way, I'm not Dimitri. I'm Heinz. Dimitri, unfortunately, couldn't make it. And it's a real pity because he knows a bunch of stuff that I don't know. But he had some things beyond his control that made him not be able to come. He's one of the guys that causes havoc on Crete when we do JCrete there. I'm the other guy, one of the other guys that causes havoc. Now that URL there, that's a surprise. If you get it before 4 o'clock, it's a very great surprise. If you are watching the recording and you get it after 4 o'clock on the 9th of May, well, it's a small surprise, right? So that's the URL you want to go to, tinyurl.com, devox19-strings. And if you go there now, before 4 o'clock, you get a great surprise. I'll have it up for a bit in case you want to get it. Now, in Java 1.1, they changed things a bit. The field stayed the same. The hash code was also still the same. And they moved intern to native code. Now, the native code wasn't necessarily faster than the hash table, and we'll get back into this whole string table in a moment. Also, to uppercase had some weird edge cases, like if you're in German and you convert the German funny letter SZ, it makes it double S, capital. This is weird stuff. But generally, most of it stays the same. 1.2, they kept the fields the same, but they changed the hash code. Now, you can imagine this was, I don't know exactly when it was, must have been about 1998 or so, 99. And even then, people were screaming, why did you change the hash code? Why did you change it? Because they had a whole bunch of, I don't know, serialized objects or something, and whatever, maybe they had some unit tests, and I mean, unit tests weren't a thing at that time, but maybe they had some testing, and all the testing broke because the hash code changed. And since then, we have not seen a change in the hash code function, or the end result. The end results, if you take a string from today, Java 12, Java 13, and you run the hash code over it, it's going to be the same answer as back in Java 2. And it's basically looking at every character now, multiplied by 31. Now, the Java 1.0 and 1.1 calculations were constant time. Constant time, which means it doesn't matter how long your string is, it didn't affect anything because at most you'd have 16 characters to look at. So it was really, very fast. Not a very good one, but very fast. In Java 1.2, it became linear time because now it looked at every character. And this, of course, could break some things. So at the same time, Java 2, there was a book written, Java Performance and Idiot Guide. Oh, no, sorry, Idiom Guide, not Idiot Guide. It was a good book for the time. But you know what it's like with performance books? The moment that they are printed, they're out of date. Because things change so quickly in the performance world, they'll tell you, do ABC, and then by the time you read the book, it's not ABC, it's DEF, right? Like all the GC tricks and tips and tricks of how to tune G1 can be replaced with use ZGC, or even better, use epsilon GC. That's even faster sometimes. That's a joke, by the way. So Java 1.3, sorry, what I wanted to say in the book, one of the big things they said was that you should never use string as a key in a hash map. You should always wrap it with another class and then cache the hash code to avoid the possibility of getting a performance degradation because of the order n calculation for the hash code. And that was Java 2, and then Java 3, they actually cached the hash code inside the string itself. So you can see it's now cached. And it's what's quite funny about that is that the string, we all think of string as immutable. The actual class is not immutable. It actually has a data race, but it's a benign data race. Because if you call hash code from 2 threads at the same time, there's a definite possibility that 2 threads will both work out the hash code. But they'll get to the same number. So it doesn't matter who writes it first. 32-bit numbers are always written atomically in Java. They're never written as 2 16-bit numbers or as 4 8-bit numbers. So it's completely safe. It's a benign data race, but there is a data race, and it's not actually technically immutable, although you can view it as immutable because it's like immutable. Now, I tried to get some of the names from Devox Poland, and got the name list here. That's also a joke, but it's okay. What do these names all have in common, besides that we got them from Devox Poland? They're all the same length, correct? What else do they have in common? Pardon, sorry? That's correct. They all have characters. This is a big O, so it's not a 0. But they're all just characters. What else do they have in common? Pardon, sorry? That's parallel talking, if you can one at a time. They all have a hash code of 0, right? Now, I generated this using brute force. I won't show you the code because it is incredibly ugly, and I'm embarrassed to show it, right? But if you want to see it, you can find it on, on my GitHub repository. And, and so what's so bad about having a hash code of 0? Well, what's bad about it is that when it's 0, if you look at the algorithm, it actually won't cache the hash code inside. That's the first problem. The second problem with having it 0 is that if I've got a bunch of 0 strings, I can generate an infinite number of further strings that also have hash code of 0. Because if I add 2 of these strings together, the hash code is again 0. Once you get back to 0, you start multiplying 0 by 31, it's 0 again, and you start from the beginning. So for example, here I've got 3 of the strings added together, and the hash code's also 0. Hash code's always going to be 0, as many strings as you want to combine. So you can generate a huge number of strings, all with exactly the same hash code. Now, if the hash code was 1, it wouldn't be such a problem, because 1 by 31 is not 1, it's 31. And so it's more difficult to generate an infinite number of strings with a hash code of 1. Let's have a look at how this affects things. So I'm going to go run this in Java 6, because that's the earliest version I've got on my machine. And you'll see here, this is Java 6, and it's running the string, and what I do is I double the size of the map, and then I look at what the performance degradation is. And you can see that as I double the size of the map, the hash code lookup, or the lookup on the map, gets approximately twice as slow. Now, at some point, there'll be a worse jump than twice as bad, but generally, we say it's linear. So if we double n, it becomes twice as slow. Quadratic would be 4 times as slow. Cubic would be 8 times as slow. But this is becoming twice as slow because it's double the size. So, of course, this is a problem. Here you can actually see it went from 2 seconds to 7 seconds. Sometimes we have these jumps in the performance degradation. All right. We'll get back to this in a moment. Very easy to attack a server by sending lots of strings with hash code 0 to the server. And then both put and get become linear, they're both linear in performance. In Java 4, they kept the fields the same as 1.3, but they introduced another interface called char sequence. And char sequence is used to abstract between string and string buffer. So if you didn't know which one to use, you could just have a char sequence for both. Plus they had things like regular expressions, matching, splitting, and a whole bunch of other really cool features. Now, before we go on, in Java 4, and before that, so Java 1.0 up to Java 4, when you appended strings together, like you said, hello plus args naught, then it actually added inside your bytecode a string buffer. It made a new string buffer of size 16, then appended hello, then appended args naught, and then did toString. And by the way, if you compile it, if you save it with Eclipse, it actually compiles slightly different code to the way it did with Java C. So, but in the same direction, similar to that. So it will make a string buffer. In Java 5, the fields were the same as 1.3, but they made them final, except for hash, of course. They also had code points where you could have 32-bit characters rather than just 16-bit characters to support the new Unicode. And they did something which was quite funny. They actually added a class to support the case where you don't need synchronization. You see, string buffer was like a vector of type char, and the string buffer is most of the time wasn't necessary. You didn't actually need synchronization because most of the time when you're adding strings together, it's within one method anyway. So you can simply, it's method confined, and you can throw away the string builder or string buffer once you're done with it. So they solved the problem by having another class called StringBuilder and basically branch off to StringBuilder or string buffer, so you could choose which one to use. And they actually didn't need to do that. They could have, in Java 6, they solved the problem in a general way. So in Java 6, with escape analysis and lock elision, I'm not sure how to say that, where they elide locks, they actually managed to get rid of the problem in a general way. But they wrote it in Java 5, and now we're stuck with having two different classes. It actually wasn't necessary. They could have just kept it like it was. However, in order to get the string builder class, we had to recompile the code. And in Java 5, what would happen is if you had handcrafted string buffer code, it would typically be slower than string builder. As I said, in Java 6, they changed a few things, so it actually was faster again. Java 6, not much changed since Java 5, except that at some point they added compressed strings. This was quite funny because you would create a string, and it would look whether or not inside your char array you have any characters that are bigger than US ASCII. So if it's bigger than 7 bits, US ASCII. So if it was bigger than 7 bits, then they would use a byte array rather than a char array. So there's some funky situations. If you're doing some profiling and you see all these byte arrays, it could be from string or maybe not. You didn't know. So it wasn't very consistent. Another thing which they added was to have optimized string concat. See, one of the problems in Java 5 was because they now had string build and string buffer, they couldn't share the char array with the string anymore. But in Java 6, when they added optimized string concat, they again could share the char array with the string builder and the string buffer and string. And in fact, since Java 6, the first question we had, because the values I was adding together were all strings, it was a special case. Because of that, it actually doesn't matter which one you took, the append basic, append string builder, or append string builder with a size, those three, since Java 6, have always been exactly the same in terms of performance. Now, the last one with the format is going to be the same speed soon. Not quite yet, but we're getting there. And there's one experimental version of Java you can already get. Unfortunately, the person who knows that is not here. He sent me the information, but I don't have it in my head. Basically, the string format is going to be very, very fast going forward. So, in my opinion, a good idea is to use string format because that is actually, in many cases, the most legible version of the four. Right. Now, we spoke about this attack vector that we have on servers, where somebody can send us lots and lots of strings that always have the same hash code, and we end up with this long list of elements. And we order n lookup on a hash map or a hash table. And they tried to solve that problem in Java 7 by having a second hash code inside string called hash 32. Hash 32 was never 0. If the hash code worked out to 0, they made it 1. So that stopped you from being nasty and generating all these hash codes of 0. Also, it was randomized. So every time you started the VM afresh, you'd have a different possible hash code, hash 32 for this. This hash 32 was only used by the hash map in order to put the strings in the table. So that's the first change. Now, when I saw that, I was really excited because I thought, now we no longer have this problem with the string DOS. And for years, I was telling people that this was now solved in Java 7. But there's one thing I didn't do. I didn't actually try it out until I prepared for the talk last year, and then I tried it out. And I ran Java 7, and you see that Java 7 is exactly the same as Java 6, right? By default. And I didn't realize that for, I don't know, a decade. I was telling people, don't worry, it's all fine in Java 7. Meanwhile, it wasn't. So if you want to do it in Java 7, you need to have the special setting -djdk map alt hashing threshold equals whatever number you want. Once the map is of that size, it starts using the alternative hashing mechanism. So it starts off at the same, and then once we grow the map past a certain size, oh, look at that. Now it goes really quickly, because now you no longer have order n lookup on the map. It's well distributed around, and these strings are not all with the same hash code, the ones that are generated before. Okay. A couple of other things in Java 7. They had a funny constructor added where you could pass in a char array and a Boolean unshared, which was actually ignored. So this constructor was called by shared secrets get java.lang access.new.string unsafe. And what you could do is you could take an existing char array and you could construct a string with that existing char array. It wouldn't actually make a copy of the char array, right? So, and I know people actually use that in production code. In Java 9, they took away our toys, and I'll explain why in a bit. The second thing that changed, which was sometimes more problematic, was that substring no longer shared the same char array as it did in Java 6 and before that, up until right from Java 1.0. And what would happen before is somebody got a big string and they wanted to they only needed part of it, so they would make a substring of that big string, expecting only to use a small bit of memory. But because the string shared the same underlying char array, it used exactly the same amount of memory as the big string. And people kept on making mistakes like that, and there's an easy way to get around that, but they didn't. And so as a result, in Java 7, they changed it so that every time you make a substring, it made a new string with its own char array. See, there's no more offset and length. So if you want to have a substring which shares underlying char array, you have to write it yourself. Fortunately, we now have a common interface called char sequence, which you can use. So you can get around it. You can make your unsafe strings with char sequence using that. And I've got a newsletter 230 you can have a look at for that. Java 8 got rid of the hash 32. Maybe they realized that nobody actually knew that you had to turn it on. So they probably thought, well, nobody's using this feature, so let's get rid of it. What they actually did is they solved the problem in a general way. They solved the problem with linear access to a hash map for all keys. Well, okay, not all keys, but most keys. And just something you need to just remember, when you have a key in a hash map, when it's a string, it's fine, don't worry about anything. But if it's your own key, make sure that that key is also comparable. You need to have hash code, equals, and comparable since Java 8. Because if you land in the same bucket, then you're going to end up with a beautiful binary tree, a red-black tree, instead of a long linked list. Let's have a look at how this runs in Java 8, this code, this string DOS. So Java 8, and just the normal one without the funny setting. And you can see that as we double the size of the map, it does get a bit slower, but nothing like before. Because I mean, if I have like 32,000 elements, that's only 15 lookups and I found the right place. Well, it's red-black trees, so it's not exactly balanced, but maybe you're going to have 30 lookups, but you're not going to have 30,000 lookups in order to find the right place. So this is a great improvement. In fact, it takes me longer now to create the map than to do the lookups. They also have some other methods for joining several strings, static methods, and deduplication is another thing which is pretty cool. I mentioned intern before. Now, if I've got two different places in my program where I've got the same constant string, for example, devox, right? There's devox in one place, there's another class with another devox over there. And it's the same constant string. When the class is loaded, Java checks whether it has already seen that devox before. And if it has, it pulls that instance out of the shared table and then uses that going forward. So if I've got multiple classes with the same string, they share the same string object. That's all shared. And we call this intern, right? This happens automatically for static strings. If you have a double quote string generated, even if you plus them together, as long as it's set at compile time, they can do this. And you can actually intern your own dynamic strings as well if you want to. But it's the same object. Now, if I make two strings and they happen to have the same content, they will not be optimized in any way, except in Java 8. Since then, you've got the option, if you use the G1 collector, to deduplicate the contents of the string. So the string is still different, but they share the same char array. This kicks in after a few GC cycles. This has been there since Java 1.8.0.20, and you can replace the char arrays of duplicate strings. Here's an example. I'll make a char array, some ketchup or something, I don't know, baked beans, and I'll make two string objects. Now, they actually will have different, the two strings will have different char arrays. You can see it. If you print out the field, you can see at the top over here that it's two different char arrays. This is the identity hash code that's being printed out. And being different means it's a different object. If it's the same, it's probably not the same object. Or it's probably the same object, but not necessarily. But if it's different, for sure it's a different object. And then I call system GC. Now, that actually does a full GC. You don't need a full GC. You just need to have a number of GCs. I think it's like 5 or 6 young GCs. And then I'm also sleeping for a while because after it's been notified that it's going to do this, it still takes some time to actually do the deduplication. And then after the GC, you can see that the char array is a shared char array. Right? So this can save a lot of money, a lot of memory. It can also cost something extra in doing the deduplication. So you need to test with your system whether it works for you or not. And another thing is that if you rely on this, that means you're going to be bound to the G1 collector, because it only works with the G1 collector. It's a special case. So if I make a new string, hello world, right? The hello world is 12 characters. And in Java, if I'm using a 64-bit compressed oops VM, then the object header is 12 bytes. The length, no, not the length, the value, the pointer to the value is just a 4-byte pointer, so that's 4 bytes. Plus the hash is another 4 bytes, the cached hash code. And this actually adds up to 20 bytes, but it gets rounded up to the nearest 8 bytes, so it gets rounded up to 24 bytes. The char array is again an object, so it's a 12-byte object header, plus 12 characters, which is 12 times 2, gives you 24, plus the length, which is another 4, comes to exactly 40 bytes. It stays there, it doesn't go to 44 bytes. And the total for the string is 64 bytes. Now, deduplication will share the underlying char array. So this means that you're going to save 40 bytes automatically. Intern saves 64 bytes, but at a much higher cost. And in fact, until Java 10, the intern table did not grow. It stayed a constant size. I think in Java 6 it was like 1,000 entries. So once you had more than 1,000, you started having bucket collisions and it became really expensive. And in Java, Java 7, they made it about 60,000, but that also was a constant size. And it stayed constant until Java 10. Since Java 11, the table does grow. It's now a power of 2. Now, there's a really neat command called, a program called jcommand, JCMD, that can show you details of what's happening inside your VM string table. So have a look at that. Now, If we write our own concurrent hash map, if you use our own concurrent hash map and use put if absent, then we have the same memory saving as with intern. However, you have potential memory leak because the strings will never be deleted from that concurrent hash map. But it's a lot faster than using intern. And it'll work with any GC, not only with the G1 GC. Right, then came Java 9. And one of the big things there was that they tried to, well, first of all, they did a sort of a study of what we are actually storing inside strings. And they found that most strings actually are only, would work with just Latin 1. And so they have a special case now where if your string is Latin 1, then they use a single byte per char rather than 2 bytes per char. So they store the strings inside byte arrays, always in byte arrays, and they've got a special coder byte that they use to say what the type actually is. And at the moment, it's either Latin 1 or UTF-16. That's your option. And the hash is also still inside there. So they changed something. This means when you're doing a profile in Java 9 onwards, you have to look for byte arrays, not char arrays, if you're looking for strings. Another thing which is a very big change is the way that they do the concatenation since Java 9. Now, before Java 9, from Java 5 up to Java 8, whenever you had a plus, they converted that to StringBuilder inside your bytecode. Nowadays, they indify this. They actually, they've got a class called a string concat factory, and this string concat factory is used to concatenate the strings together using invoke dynamic. Now, if you, in my previous benchmark, I cheated a bit because I showed you the example where we were simply adding strings together. Now, when you're adding strings together, it doesn't matter what you use. StringBuilder, string buffer, sized, plus, it's all the same. But it is different if you've got mixed parameters. And here I've got mixed parameters. I've got some strings, some long, some double, some ints, all mixed together. And in that case, you can see that the string buffer size in Java 6, the string buffer sized is the fastest, right? StringBuilder and plus are exactly the same. And this is the same with Java 7 and Java 8. It's all exactly the same, where the string buffer sized was the fastest. But this is only for mixed parameters. If it's all strings, it's the same as performance. But if it's mixed, that was faster. The concat, that's another option, was always quite slow. And then format has always been horrible. But as I said, format is going to be the same speed as plus going forward in the near future. Java 11 results, you notice that the plus is now much faster than the other options. Okay? And of course, you have to recompile it with Java 11 or Java 9 onwards. So if you've got Java 8 code, it won't run faster just because you're running it in Java 9 because it's going to be using the SB, the string buffer, the string builder over here. They've actually got 6 different algorithms. They did this in order to be able to test and compare. But the fastest is the default, which is the method handles inline exact, where they figure out exactly what the size needs to be of the byte array. They create that byte array, and then they fill it with the values. So there's only one object being made. And the interesting thing here is the number of bytes that are constructed. You see that for the inline size exact, you have the least bytes being made. So it's only 152 bytes per operation over here. So there's no reason to change this. It's the default is the best, obviously. Well, that's what you would expect that. But the other ones are just for debugging purposes. As I mentioned before, they changed the char array to be a byte array. And this saves space when your characters are Latin 1. You can turn it off if you say minus compact strings, but by default, it's on. And actually, if you've got a language that is not Latin 1, like Greek or something like that, or special Unicode characters, then the maximum length is actually half of what it was before. Because before it was, you had one char per character. Now you've got 2 bytes per character. So, but I mean, that's only going to affect people who have very large strings. Compact, non-compact strings. It actually seems like having compact strings on is a bit faster. It certainly uses less memory. So it's something you just want to normally keep on. There's no good reason to put it off. One of the interesting things with string is that you've got all these methods like index of equals and hash code. And when you look at the code, you sometimes scratch your head and you go, why are they doing it like that? And couldn't you write it better? But in actual fact, the code that you see in the Java code is not the code that's called. In Java, there are quite a few methods which are marked with hotspot intrinsics. And that means that it can be exchanged with handcrafted assembler to do it faster. This was in Java 8, and in Java 11 you've got far more strings because now they have to support either Latin 1 or UTF-16. And what Dimitri and I did was we looked at equals, and we said, what does equals actually look like? This is what string equals look like. It was a lot simpler before, but now we have to support these different encodings, so it's more complicated. And if I'm trying to compare 2 strings, let's say they're Latin 1 numbers, Latin 1 strings, it's going to it's going to call string Latin 1.equals, which, if you are able to zoom into this, is somewhere in here, Latin 1 equals, I don't know where, there it is, Latin 1 equals. So it's in there somewhere, inside the intrinsics. And this is actually what the code looks like, the string Latin 1 equals. And at the top you see hotspot intrinsic candidate, which means it can be exchanged for, really, really fast C code, assembly code, whatever. And but if you look at this, what they're doing in the Java code is they're going through both arrays, looking at the bytes one at a time. One at a time. And I'll get back to this in a second. What I want to in fact, I want to just show you the values down here. So if you take a string of length 4, and you can see that doing it with normal equals and hand rolled is about the same speed. But as the length gets bigger, like look at length 256, all of a sudden the string equals is like much faster than the hand rolled one, where you're iterating, basically copying and pasting their code and using their code. Actually, the Java code is much, much slower. And the reason is that inside the intrinsics is probably implemented with something like arrays.mismatch, which uses vectorization to compare a whole bunch of bytes at the same time. So you can get a massive speed up with mismatch, arrays.mismatch. And yeah, vectorization is a great idea. For some reason, they don't actually take into account deduplication, so they don't check whether the array is the same. They should do that, but they don't. Don't know why. So we've actually gone a lot faster than I expected. So we can look at some demos, because there was a demo I wanted to show you. But let me just open this again. And whilst we are doing that, do we have any questions? Any questions about string? So here's another interesting little thing that I found. There was a program, this must be closed, that's the wrong, okay, let's try that again. There's a program where they were comparing 2 strings. And they were comparing the strings using index of. So somewhere in here, there's index of comparison, which is basically, where is it now? Here it is. If type.compareTo primitive type equals 0. Now we know that compareTo, if compareTo equals 0, that's equivalent to equals is true, right? Anybody disagree with that? Who disagrees with that? Who thinks compareTo equals 0? Or rather, let's ask it differently. Under what circumstances can compareTo equal 0, but the strings are not equal? Anybody can think of a reason? Yeah, exactly. If you've got compareTo implemented wrong. Absolutely right. But the compareTo actually really just compares the strings. And it used to be just the Latin one, compare, which will look like this, right? compareTo iterates through and compares all the characters. Okay. It was actually, the problem was under Java 7 and 8, so the code looked a bit different to that. In fact, let's go to Java 7 and 8, you'll see it. Let's go to Java 8. Before we had the different encodings, so compareTo was much simpler. So this is what compareTo looks like, assuming this is correct. Assuming that you're going to get, character comparisons. And I can't think of a reason, and neither could anybody else. And what actually happened was, what we think happened was, on this one particular machine, there happened to be a race condition between Intrinsics and the interpreted Java code. And it happened to kick in sometimes at exactly that point when compareTo was being called. So sometimes compareTo would happen to come back with the wrong answer, with 0. It was a very weird, freak example. And actually, once they changed the hardware, the problem went away. They didn't have that problem anymore. But it was very strange. And what we did was we turned off the intrinsics. We basically said, you can do that. You can say -XX disable intrinsics, and you say what method you want to disable. And then it turns off that, for that particular method, it turns off the intrinsics. Okay. That was quite interesting. I want to show you also this really, really useful J command. So I've got IntelliJ running, as you can see. And if I say JPS, you can see the process. I happen to know that the process that is being used is 9872 for IntelliJ. But something I discovered yesterday, quite by accident, was that you can now say or JStack, for example, and I didn't know that you can actually put in the name of the program. Did anybody know that? I didn't know that. I always thought you had put in the ID, the PID. So for example, JStack Gradle daemon will show you, we'll do the thread dump. I was always trying to type in the number, which is really, really painful. So you can also say jcommand of that Gradle daemon. And when you type jcommand of the process ID or the process, it gives you a list of all the supported commands you can send this J command. So for example, one of them is vm.string table. So you can connect to VM string table. You can say Gradle daemon VM string table, and it shows you the number of buckets, which is 65,536, so it's a power of 2, the number of entries which are currently in there, and the fill factor. Now, this is an incredibly useful thing for debugging. If you find that you have poor performance on the intern, if intern shows up as your bottleneck, have a look at what's inside there. Now, as I said in Java 11, that changed it. It used to be some weird number, like 60,000, but they changed it so that it would be dynamically growing as you need it. So if you have more and more elements in there, it's going to make it bigger. So that's quite useful. It also shows that the maximum bucket size is 5, so they never have more than 5 elements inside a single bucket. So that's also quite useful. And if you really want to know, you can say minus verbose, and then it shows you all the strings that are inside the string table. So if you want to know what's actually in there, you can do that. You can debug it that way. So that's a good thing to know. All right. Any other questions, comments? All right. So let's look at this. Oh, yes.
With regards to the duplication, so going through and removing strings which look the same, is this applied to all strings in regards to how they're created? So
Yes.
you create a string literal or you create a new string, it's just applied to all strings?
Right, so I'll repeat the question. The deduplication, is it applied to all strings, regardless of how they're constructed? And the answer is yes. So if I've got a constant string, and I make other strings from that, or I make other strings that happen to have the same characters, it's going to have the same. And you can see that over here in the, let me quickly show you that benchmark, or that code. That's deduplication is, where is it now? I don't know if I've got it here. Oh, well, I don't have it here in here, but yeah, you can try it out. It's going to be the same. And the string will be deduplicated before it goes into the old space. Once it's in the old space, it'll never be, like if it misses it, it won't try it again. So just to summarize, use plus instead of StringBuilder wherever possible. We don't want to use StringBuilder, we don't want to use plus. Unless, of course, you have a long loop with plus equals in the middle. You do want to use StringBuilder, but nobody ever writes code like that. So, you know. Instead of using intern, if you can control what the strings are going to be, rather use your own cache, like a concurrent hash map, or use string deduplication if you're using G1. Hashing can be expensive on strings because it can be linear, and there's really nothing they can do about it. One thought that I had was to pre-initialize strings with another value, but the problem is that will cause possibly a data race, and you absolutely cannot afford to have a data race on string. String is such an important, like a non-benign data race, a dangerous data race. You cannot have that. It's a very, very important class. Also, strings, since Java 9, have been using byte arrays instead of char arrays. So it might use less memory, probably will use less memory than before, especially if your strings are Latin 1. If they're not Latin 1, well, it's going to be the same. And even if one character is not Latin 1, it's going to use UTF-16. And this is done automatically when you're loading the string or creating the string, it automatically figures out what it is, and then it uses that. And does some other funky things inside there. One of the things where things might be faster is in comparisons, because if you've got two strings and one of them happens to have another character, then they would have a different encoding, and it would automatically not be equal. So that makes it a bit better. And all the benchmarks that we've written so far seem to indicate, I'm being very careful because it's a benchmark, they seem to indicate that there's no performance degradation of using, of having these two different encodings rather than always a char array. However, I'm not sure if this is a Volkswagen or not. I almost suspect it's a Volkswagen. It's like they somehow detect that when I'm testing it, and then they're like, give me better results. Because in other benchmarks where I combine it with other factors, it seems to make a difference. Right? So you might pick up a difference in performance if you are getting characters from strings. Java 8 versus Java 9 might get slower. But we haven't managed to isolate a micro benchmark that proves it. But maybe we have to take the string for a drive and test it whilst we're driving. I'm not sure exactly how to do that. Any other comments or questions? We've got about 20 seconds left. All right. Thank you very much for listening.